So we'll quickly do a little bit of probability, very, very quick, because that will be very relevant for everything we do. Yes, and we are running late, so I'll do it quicker. If you know probability, if you're brushed up, please snooze for a little bit. What is the probability? You pick a ball from pin P1. What is the probability that the ball is red? Guys, I tell you that it's pin P1. X equals red given pin P1 equals half. Perfect. Very good. You're all comfortable, right? Only I want. Okay, now if I ask you the other question. A red ball has been picked, and I ask you, what is the probability that it was picked from pin P1? What would it be? 3/7, because one way to think of it is there are 3 balls here, 4 balls here, 7 balls total, right? 3/7. Right? Very much true. But another way to do it is, anyone? Bayes rule. P given X is equal to P of Px given Px, which is equal to P of X given B, Pb given divided by Px. What is P of X given B? This is exactly the same thing, right? Half. Pb is how much? This is bin 1, right? So Pb, what is the probability of picking bin 1 given that there are 2 bins? Half, assuming that the probability of picking the 1 bin is uniform. So this is half. And what is Px? Oh, we don't know what Px is, right? So what we can do is we can write Px as Px. Okay, let me write this properly. What does this mean? This is Px. This is a joint distribution of X and B. This is called marginalization. And then we can write this as sigma P, X given B, Pb. If you've seen the cheat sheet, this is what we did. So this is marginalization, marginalize, and this is Bayes. Clear? So Bayes says this is posterior. By the way, this is called posterior. Posterior is likelihood times prior divided by evidence. I'm hoping people are familiar with this. And if I then ask you, are you all familiar with likelihood and posterior? Very good. If I ask you, probability Illinois resident given that it's a Harris voter, is this likelihood or posterior? And I'm going to ask you the same question for the next one. Okay, let's do this one. P Harris, probability of Harris voter given Illinois resident. And suppose someone gives you the distribution of voters of Illinois. Then, can you say which one is likelihood, which one is posterior? I know the distribution of voters in Illinois. And now I'm asking, what is probability of Harris voter given Illinois resident? Likely. This is likely. Okay. Like one way to remember is likelihood is always easy to calculate. You know the distribution. You just have to take a point and compute the probability of that. Always easy. If this is likelihood, you know this is posterior. But try to calculate this. I tell you, Yulin is a Harris voter. He's a Harris voter. I tell you that. And now I ask you, what is the probability he's from Illinois? Right? See, it's hard, right? He can be a Harris voter if he's from Illinois. He can be a Harris voter if he's from Texas. He can be a Harris voter if he's from DC. He can be a Harris voter if he's from California. So you have to look at all those probabilities and then figure out what is the probability that he is an Illinois resident. Okay. So this is like saying B given X. You have to look at all the B's. If I tell you X is a red ball, you have to look at all the B's to figure out. Same here. If I tell you Illinois resident given Harris voter, this Harris voter is like a red ball. Illinois resident is like pin P1. You have to look at all the possible pins how much the probability is from all the possible pins, and from that estimate. Hope this is clear. Okay, good. So in general, you should think of likelihood as, and maybe this is a easier way to understand. I give you data and I give you some distribution parameters. Distribution parameters, let's say for a Gaussian, is some mean theta and some variance sigma square. If I give you the parameters theta, meaning I give you the mean and the variance, and then I give you some data point x, what is the probability given those parameters? Oh, that probability is this value. Right? That's likelihood. Posterior says, I give you the distribution parameters theta, sorry, I give you the data x. What are the distribution parameters theta? Which means I take this axis and I say there is a data here, there's a data here, there's a data here, there's a data here, and so on. And now I tell you, okay, fit a Gaussian to this. So now if you take a Gaussian, you need to figure out what the mean and variance of this Gaussian is that best explains that data. So one way to do that is to move that Gaussian back and forth to best explain the data. Make sense? So that is posterior. I have the data. I'm trying to figure out what distribution this data came from. So I'm going kind of backwards, posterior. Likelihood is you've given me a distribution and you're saying how much is the probability of this data. That is easy. Okay. Good. Prior means what is the probability of these distribution parameters? This distribution, the ball could come from pin P1, the ball could come from pin P2. What is the probability of pin P1? What is the probability of pin P2? That's prior. And evidence is what is the probability of the data. It doesn't come up too often. Okay, so we are going to do a quick review of maximum likelihood. So guys, now I tell you, there's an opaque basket and there are a bunch of colored balls in it. Okay? And I pick balls from that basket and I put that ball back. And every time I pick the ball, I look at the color and I record it. So here is what I see picking 10 balls from that basket. Blue, red, red, green, green, blue, red, red, blue, blue. Okay? This is the data, right? And now I ask, can you estimate theta, where theta is the probability of drawing a red ball? Do you see what I mean? So how would you do this? So the way you do is, hey, is this like, am I asking you for the likelihood or for the posterior? Posterior, right? Because I want to know what that probability of drawing a red ball is given the data that I have, right? Very good. So the way to do this is you're basically asking what is the probability P of x1, x2 all the way till x10 given theta. Okay. And this is called the likelihood function. Okay. If I do the balls independently, then I can write this as P of x1 given theta, P of x2 given theta, and so on, P of x10 given theta. Which is, I can write this as product of I equals 1 to 10, P of xi given theta. Make sense? Because I drew the balls independently. And then what I'm going to do is I really want to maximize this L theta. I want to find the theta that will maximize the product of these probabilities. Right? So what should I do? I basically want argmax theta L theta. Right? So how do I find argmax theta L theta? I do del L theta by del theta. I basically differentiate this with respect to theta. And this probability Pxi given theta, can someone tell me what it is? If that xi is blue, then it's 1 minus theta. If that xi is red, then it's theta. See, okay, I see some confused faces. The ball is blue. That means I didn't draw a red ball, right? What is the probability of that? If theta is the probability of drawing a red ball, then 1 minus theta is the probability of drawing any other ball that is not red, right? So Px1 given theta equals 1 minus theta. What is Px2 given theta? where x2 is a red ball. Theta, right?
Sorry, maybe this is old stuff, but isn't it probability of drawing a blue ball something less than 1 minus theta because you drew a blue ball and not a green ball?
But it is some ball that is not red. So when you take this product, you will get theta square 1 minus theta to the power, sorry, not square. How many red balls? 1, 2, 3. The theta cube, I think I got it. Or 4 red balls, theta 4, 6. Okay. And then I differentiate this with respect to theta, equate it to 0. Whatever theta I get, that's my best theta. If that was not clear, this should make it clear. We're now going to do this in 2 dimensions. Okay. Imagine a satellite looking at the world, and it sees bees, and the bees are basically distributed like this. That's the satellite picture of bees. So the data that the satellite has is the location of the bees, which is L1, L2, L3, all the way till L10. Okay. And now you know somehow that the bees have a beehive, and the bees fly away from the beehive in some Gaussian distribution. Okay. So there is some beehive somewhere, and they're flying around the hive, and that distribution is Gaussian. Okay. That Gaussian distribution is parameterized by mu and variance, mean and variance. And I ask you, what is the beehive location? Basically, the question is, what is the beehive location, given that I've given you the bee locations? And you know that bees fly as a Gaussian. Basically, the bee's distance from the beehive location follows a Gaussian distribution. How would you solve this problem? This is a maximum likelihood problem. You basically ask this following question. I'll take a Gaussian dome, I'll put it somewhere, and I'll ask, if this Gaussian dome is correct, what are the probabilities of each of these bees? Right? If I place let's say this is the bee's location, and I place the Gaussian dome here. Do you think the probability of the bee locations are high or low? Very, very low, right? Because the bee locations would be this value, this value, this value, this value, all these values, right? All of them are low probability. That means you've put the Gaussian dome at the wrong place. Agree? If you move that Gaussian towards this direction, you think the probabilities of the bees will increase or decrease? Increase. So maximum likelihood is saying, figure out that distribution by moving it around so that the probabilities of all the data becomes higher and higher. Right? So if you bring it somewhere here, that probability will be the highest. And then if you again bring it over here, again the probabilities will go down. You agree? You're trying to find where is the best spot you should put that Gaussian so that all the probabilities get maximized. And this is the intuition behind maximum likelihood. You're moving around that distribution that you want to learn to best explain the data. And best explaining the data means the probability of all the data may be multiplied, gets maximized. Good. And you see, we will do this with neural networks where instead of this Gaussian, this will be a neural network. So there is a bunch of images instead of bees, and we have a neural network. The neural network learns some complicated function. And we say, hey, neural network, can you move your function around? What does moving your function around means? Changing theta. What is theta? All the parameters of the neural network. Right? So you say, hey, neural network, can you move yourself around, which means change the function around so that your function best explains or maximizes the likelihood of all that data. This is what generative models are after anyway. Okay? So very good. I hope you understand that if you see that animation once again, the Gaussian moves, and at the best place you see the mean of that Gaussian is this, and you say that's the beehive location. Good. Question for you. Now the satellite sees two colored bees, red bees and blue bees. And it wants to estimate the beehive location for red bees and the beehive location for blue bees. How would you do it? Solve them separately. You have a red Gaussian, you have a blue Gaussian. Take all the red points, take the red Gaussian, move them around. Take all the blue points, take the blue Gaussian, move them around. You got the best beehive locations for both. Okay? This is no different from the previous one. Very nice. You solve the red Gaussian, solve the blue Gaussian, you got two parameters. Here is the hard question. Suppose I say the satellite can no longer see the colors, but there are two colors. There are some red bees and there are some blue bees. Now tell me what are the red beehive location and the blue beehive location. Any ideas?
I know they're all colors.
Only two colors.
Sure, yeah.
Sorry?
Mixture of Gaussians.
Mixture of Gaussians, but how do you solve it? Four para. Oh,
Yes.
That's a little bit difficult. Sorry? You have two Gaussians, but where do you place the Gaussians? Right? If you place them randomly, then what do you do? Huh? But okay, so you see, let's build up this idea quickly. No, that's totally fine. You place two Gaussians randomly. Okay. And now this is the red Gaussian, this is the blue Gaussian. Which data points are you going to calculate probabilities for? Any given point, are you going to assign it to red or are you going to assign it to blue? You see, right? In the previous question, it was easy. You had two Gaussians, you took the red and you assigned it to red. You took the blue and you assigned it to blue. But in this case, even if you have two Gaussians, how do you assign? Okay. So this algorithm, which now Yulin will take over, could co-optimize what and what? But when you calculate the probability, you have to take each B location and you have to say this black B, is it actually red or is it actually blue? What will you do there?
Consider this point to be associated with both of them and take the summation of them and then maximum.
Perfect. Okay. So this algorithm is called the expectation maximization algorithm. Very, very powerful. My feeling is if you know expectation maximization well, you will see many problems that you work on which you can apply expectation maximization. Wireless signals mixed with interference, it's like black dots. You want to separate signal and interference. Many places you can apply this. And the whole intuition is, you see, right, this is the chicken and egg problem. The whole intuition is, I'm going to start with some Gaussian, and for every black P, I'm going to think of it as a random variable. Meaning, it has some blue, some red, and I'm going to jointly optimize how much red, how much blue it has, and where the Gaussians lie. I'm going to do it together, and I'm going to come up with an estimate. It's called expectation maximization. Time for Yulin to take over, but while he sets up, any questions? Yeah. Do you need to know the number for the number of P's? No. Number of colors you need to know. Yes. But no, but what we will talk about, we'll assume we know the number of colors. Expectation maximization can work with infinite number of colors. And I want to just give you one sneak peek. Ready? Yeah. The sneak peek I want to give you is, this is connected to VAE. Can you imagine how? The number of underlying rules will basically say whether these bees are red or blue or what is the problem. That is the rule. We can't see the rule. If I show you this data, you don't know the rule. You don't know whether it's red or blue. But there is some latent distribution that tells you whether it's red or blue. Or you can learn that. And you learn that distribution which maximizes the line. Again, rough, but I want to kind of prime you with what to expect later. This is why we are looking at this algorithm, because this will be the foundation for variational autoencoders where we are tracking down rules.
Yeah. So just to add to Rahman, the relation between EM and variational autoencoder is that you can see that the color in variational autoencoder, the rules can explain the image. Now, if you have the color of the B, it can explain the location, and that's how we make the analogy. Okay. And also, I want to add to one previous very excellent solution proposed is, hey, why do we just treat these samples as same color, just black color, and we just fit a mixture of Gaussians to that? Like we already know there are two Gaussians, right? So we can look at the mixture of Gaussian is so mixture of a Gaussian is also a family of distribution, which I have mean, I have variance of each of the Gaussian. But then you have to model a lot of parameter. I will give you a very quick example. The blue hive and the red hive may not be of the same size. There, among all these bees, there might be only two bees from the blue hive. In that case, this Gaussian of mixtures will be very, very unbalanced. You will have a very small Gaussian and add another big Gaussian. So in that case, it's very hard for convergence in Gaussian of mixtures. Okay, and that comes to some of the solution I want to first mention. Honor, I would say honor. For example, K-means. K-means is a very famous application that when you come to classify your data, if I'm telling you, I'm asking a different way. Now this is your homework, and then I ask you to group them into two different colors. If I ask this way, maybe you will come up with, hey, I will do K-means. I pick two random centroid, and then assign the bees to the closest centroid, right? And then according to that, I move those centroid to the center of each of the assigned cluster. That's called K-means, right? But the bad thing of K-means is that, hey, each of the bee belongs to their closest centroid. This you can see from Gaussian is not true. I'm a blue bee, but there's a smaller probability I fly away from my hive, but now I'm closer to a red hive. But I'm still a blue bee. You cannot call me as a red bee, right? So that's where we want to do the maximum likelihood estimation. Before we go into that, I want to emphasize maximum likelihood is not a way to calculate likelihood. We already told that likelihood is very easy to calculate. So actually, maximum likelihood is a way to calculate posterior. Maximum likelihood is a way to calculate posterior. Okay, sounds confusing, but that's it. Okay, now the question, let's formulate it. Given the beehive location X, we want to estimate two parameters. One is the color of each of the bee, and the second is the beehives. Now, the observation we found is, hey, we can estimate the color if we know the location of both hives. Why? Likelihood, right? Let's say if we have two hives, one blue hive in the left, red hives on the right. Now I'm a cute bee in between. Okay, I'm asking what's my color? Probability of me belongs to a red hive. Following Bayes, PZ given X. So ignoring theta now because they are all conditional on theta. Okay, we're all conditional on hive location. PZ given X equals PX given Z, PZ divided by PX, right? And then all conditional on theta. What's this term? The numerator is saying how likely a red bee is being here. So that's basically the likelihood times the prior. And I would like to echo what I previously said. Note that there's a PZ term here. PZ equals are on the numerator. What is this? This is how large the red hive is. And then in EM, we were going to also estimate that. But then on the denominator, it's like how likely a general bee is here, PX, right? how likely is a bee is here, regardless of its color. As we say, Px normally we cannot directly see. So let's open it. We marginalize it over a red color and a blue color. Okay, so Px equals Px given z equals r, or P plus Px given z equals b. Right? Because one b can either be red or blue, and times their prior. Now we will be able to calculate that because we have the red hive location, and then I know this bee is red. Given its location, I can tell you what's the red bee likelihood from Gaussian distribution. So we will know this term, we know this term. And red hive size, we will tell you how to estimate that later. Now, given this observation, we know that, oh, we have the hive locations. But if we know the hive location, we can estimate the color. But now, how do we know the hive location? EM is saying, take a random guess. Take a random guess. So we will start with a guess, saying that, hey, if the red hive is like this, and the blue hive is like this, then let's assign a color, and we will iteratively optimize that. And now it looks like a k-means, like a k-means, right? K-means also similar. I have a centroid, and then I will iteratively move my centroid. Here is similar. I take a guess. How large is the hive? What's the Gaussian variance? What's the Gaussian mean? And then I assign the color, and then I optimize that.
So just to be clear, right? Once, if I pretend I know the two Gaussians, I know I can assign colors to the bees. Right? Depending on where the Gaussians are. If I know the Gaussian, I can assign colors because the color of the bee has some probability of being red, some probability of being blue. Then I know. Once I know the color of the bees, then I can update where the Gaussians are. Right? That's the idea. So I'm going to start with pretending I know the Gaussian, and then I'm going to keep on.
Yes. So, and the key thing is that this is our first chicken. So recall, we say EM is a chicken and egg problem. Now we randomly start and we say, hey, this is our first chicken. And let's start evolving. Here, I'm going to give you a step-by-step what EM is doing. First, we say given a hive location, we can calculate the bee color. We already derived this equation, right? And that's it saying, here I mark all the bee location as purple, meaning at this point, I didn't know their color. But first, I take a random guess of where these distributions are. And now, based on the probability, I can color them. For all the left arrows, you can see it's blue color. I think there's some the resolution issue with the projector. But the left arrows are blue colors. The right arrows, they are red colors. The middle, you can see the middle arrow, it comes out back 60% blue, 40% red, right? And that's where we model it as QZ, meaning that, hey, this for this bee's color is 60%, it belongs to 60% blue, given its location, PZ given X, and all this distribution, it has 60% of being a blue bee, 40% being a red bee.
So related to the second term,
Yes.
what is the initial guess for that?
In most of EN case, we will assume each of the hive is the same, but in next M step, we will update that.
So you have an initial guess for that.
Yes, you need an initial case for that. Yeah, normally we will assume it's uniform, but soon we will see how we update that. Now we assume we have the color of each of the bee, right? So we can estimate where, based on all these color of the bee, we can update our hive location and hive size. So here, for example, if I'm asking you, hey, given this location, which hive is larger, blue hive or red hive? Blue, right? Because there are 4 blue bee, 4½ blue bees and only 3½ red bees. So this is where my PZ given R or PZ given B is going to be updated. And also, I am based on the location of these color bees. Raman already clearly say how we do maximum likelihood, right? Based on the color of bee, I also run a maximum likelihood. But of course, now notice that there are some strange samples here. A bee is being 60% blue. So this bee will only count 60% weights when doing maximum likelihood in this case. But very similar. It's just that some of your sample are weighted. Now I can move my, I can move, I didn't move, oh, sorry, here. I can move my blue distribution here. And then using this blue distribution, I will recolor my bee. So back to the expectation step. Now, because the centroid is updated, this bee will change its color, right? Because now it's in the middle of blue and red. So I should color it maybe even more towards red. And then I do this over and over again until it converges. And this is called the expectation maximization. Questions? So you can see that I start with a random chicken. I let it to born some egg. Based on the egg, I calculate the maximum likelihood. And then I get a new chicken. And then I ask this new chicken to born a better egg. And hopefully, after some iteration, Darwin told us that after some iteration, this chicken will become delicious to be eaten, right? Okay, so I mean, basically that's how it goes. Yes. Sorry? Yes. So the question is it guaranteed to be, will it always converge? In most cases, it will converge, but it's converged to a local maximum. So it's not guaranteed to converge to a global maximum. It converges when you can see, right, your maximum likelihood is not moving. But this might not be a best assignment. It's super sensitive to your initialization. Yeah.
I don't know if it's super sensitive, but there's a lot of work, many decades of work on N, but it still has sensitivity to your initial guess of theta 0. So where you start the Gaussian, it depends on that. In most cases, it converges, but in some cases, it doesn't. Yeah.
Is there any example of the speed of that?
There is lots of work.
Yes. Okay. So we have already given you a teaser on, hey, how expectation maximization can be related to BAE. In the expectation maximization, we are solving the colors of each of the B. And in BAE, we are going to say these colors or these rules is going to best explain the images we see. And that's where we are saying, later we will see BAE is nothing but you use a neural network to solve the maximum likelihood step of EM. Questions?